Hello everyone. Good to see you again. But today as a speaker, they're co-organizing. My name is Simon, and this is
Catherine.
and we'll be presenting on our recent work, generalizing from simple to hard visual reasoning. Also joint work with Abhishek, Dingley, Anirudh, and Sanjeev. So the overview of the presentation today will be, we will first motivate our project, then we will present our main findings on how to transfer good reasoning capability from the text modality to image modality. Then we will discuss why our proposed method seems to work good based on our studies on gradient alignment. Then we will conclude with some future direction. So a recent trend in the language model side has been to extend these powerful LLMs to also process image input. And there have been some proprietary efforts and open source efforts. But for the scope of this project, we decided to focus on open source models because the architecture is known to us. Proprietary models are not really known to us, so we don't really know how much analysis we can do there. So just as a recap, this has been presented multiple times in the PLI series as well, but this is something called the lava architecture. It's one mainstream way of trying to have the LLM also process image inputs. And the way it works is we process the image input through a pre-trained vision model. And then we get the output embeddings of that model. Then we process the language separately through the tokenizer and the input embedding layer. Then we have the embeddings of the text side. But they're in different space. So we just have another adapter that maps the image embeddings into the text embedding space. Then we push it through all the rest of the layers of LLM and just generate text out of it. And this has been known to work well in general, but people have been questioning, do these VLMs reason well on both the text side and the image side? And the answer is no. A lot of recent works have shown that there is some modality imbalance, where the models are not as well, don't perform as well on image inputs. So here's a concrete example. This is with ChatGPT. We provide an integral question in complete text form in LaTeX, and the model is able to answer correctly. But if we provide the same question, but in a screenshot in an image format, the model gives an incorrect answer. And an interesting finding here was that it is able to convert to the correct text first, but even after converting it correctly, it still fails to reason to get the final answer. So there is something interesting going on with these vision language models. So the main questions that we start our project with are these two questions. How are we going to systematically measure the difference of the model's performance on text and image? And we propose that we are going to measure how well the model generalizes to out-of-distribution text versus out-of-distribution image. And the tasks that we choose for this project are very challenging reasoning tasks that require the model to look at multiple parts of the image sequentially and go back and forth between the reasoning step and the image input. And all of these tasks have two difficulty levels, something that we named very conveniently simple and hard. And all of these tasks could be given either in text format or image format. And an illustrative example we have here is something called the consecutive table readout. So we have a table that could either be provided in the LaTeX table format, completely in text, or just an image of that table. And the model is asked to list off the numbers that are highlighted in that table sequentially in row major order. So from A, B, B, A, B, B. And we have these simple examples where the tables are small versus hard examples where the tables are large. And we train on simple examples and see if the models are able to solve the question on harder examples. This is something that is known as linked generalization and has been studied in LLMs before. And we just want to see how the model does, how the VLMs also perform on this on two different formats of the task. And we call this generalization behavior simple to hard generalization, or to abbreviate, we just call it S2H. Any questions so far about the setup here?
You focusing just on like lava style or also?
Yes, so we are going to go in there, but it is we worked with Eagle, which also built on top of lava, but uses multiple visual.
So you wouldn't expect. Do you expect the same phenomenon to hold for like GPT-4, the kind of like natively multimodal model?
So that's an interesting question. We have not yet attempted to do that. We have tried with other models like Y3 Vision, where like we know the architecture and we know the training data that was trained on, but like these models were not able to generalize well on these challenging reasoning tasks. That's why we focused on the model that was able to give some interesting signal. But like we are excited to try this on other models like Llama 3.2 now has a vision part, and they're probably.
But Llama 2, I think
it's also
vision is still not native, right?
It is not native, yeah, but we would like to extend this to other architecture styles in the future. Any other questions? Okay, so we will see later that the model is able to generalize well on the text format. By training on simple text, it does well on hard text. But when training on simple image, it doesn't generalize well to hard image. If we just do think of a naive way of training. So just as a summary of what we're doing here, we are going to try to measure the modality imbalance of VLMs by looking at how different they be generalized on two different styles of modalities. And later on, we're going to extend these tasks to other synthetic settings where this is an arbitrary readout pattern, very similar to consecutive table readout, a grid navigation where the model has to go from a start cell to an end cell while avoiding all of these obstacles, but collecting all of the objects in the middle. And a visual analogy where the model has to apply analogical reasoning to the two given in context examples and apply the same reasoning to the query example. And all of these tasks will have a simple version and a hard version, and we would like to see how the model generalizes to hard. And just as a note, these tasks are hard in image format. All of the frontier models out there completely fail on even the simple images. It is an interesting finding that we can still induce some kind of reasoning behavior on these synthetic settings as well. And the main idea that we'll run through this presentation will be to use the reasoning capability that exists on the text side and transferring it to the image modality. Then I'll hand it over to Catherine for the next one.
Okay, so I'll present the main results today, which is how we transfer strong reasoning capabilities from text to image modality. So the motivating question here is that as we previously observed that VLMs performs recently relatively better than on text inputs, how can we achieve similar performance on image inputs? So our proposal here is to train a model with mix various types of image-based, text-based, and most importantly, image reasoning via text conversion supervision. So just to introduce the general setup here, so we use a model that we call Eagle X2 Llama 3 AB that uses Llama 3 AB instruct as the base LLMs with two vision encoders. And the various type of supervision we're considering here consists firstly the basic unimodal type of supervision, which we call text and image. Essentially, the model are just like taking the text or image formats of the inputs and then perform reasoning through chain of thought and then predict. And we want to leverage the model's reasonably well reasoning capabilities on text inputs. That's why we consider the next two types of supervision. The first one we call image via text. So the model will be given the image format of the inputs. It will firstly ask to explicitly convert the image formats to the equivalent text format. So here it converts the the image of the table to the LaTeX, to the corresponding LaTeX code, and then it performs reasoning to chain flop and then predicts. Text, and the second type of supervision is called text plus image, which is essentially train the models on an equal mixture of text and image supervision. And finally, this is our proposal called the mixed supervision, which trains the models on an equal mixture of text, image, and as well as image via text supervision. So as Simon previously introduced, this consecutive table readout, we train the models on the simple splits, which essentially consists of the smaller tables and requires the model to read shorter length of cells, and then evaluate the models on the harder splits, which contains like larger tables and requires the model to read longer sequence of cells. Specifically, we consider two level of hardness here. So there's a slightly hard split that it's doing like a little bit of a lens generalization and a much harder like lens generalization, which requires the model to read much longer sequence. So we firstly observed that so here is the results. The first rows are representing the slightly harder version of the task. The second row is the much harder version. The first columns is the text evaluation, so evaluated on the OOD text, and then the second column is evaluation on the OOD image. So we first observed that our models achieves good S2H generalization on the text inputs of like at least 80% accuracy, but their performance on the equivalent text inputs are lagging behind. And specifically, the gap becomes wider as the reasoning task becomes more challenging. So we want to leverage the model's like better reasoning capabilities on text inputs to have like similar reasoning capabilities on image inputs. So we compare the image plus text as well as the image via text supervision. So we found that image via text supervision can actually better transfer the reasoning capability from text to image, but it comes at the cost of a higher inference cost, because during inference, the model will explicitly convert the image formats to the equivalent text formats every time for each of the samples. So that significantly increases the generation time. And lastly, for our proposed mixed supervision, we noticed that it can completely closes the gaps for the slightly harder version of the task. So it can achieve comparable performance on both the OOD text inputs as well as the OOD image inputs. And it significantly improves the S2H generalizations on image on the much harder version of the task. And also note that the same conclusions we repeat the experiments for another simple visual analogy test. We abbreviate here, but if you're interested, please refer to our paper. And meanwhile, our mixed supervision can maintain the inference cost, because at the inference time by default, it will not explicitly convert the image to text. Just to summarize this part, so on consecutive table readout, we noticed that current models can S2H generalize on text inputs, but struggles with S2H generalization on image inputs. And explicitly teaching the model to convert image to text formats can help the S2H generalization on image, but requires much more inference compute. And lastly, our proposed mixed supervision closes this modality gap phenomenon and maintain the inference.
Yeah, so in the illustrative example of the consecutive table readout, we have the model that was already able to generalize on text. So all we had to do was just use that and bring it over to the image side. But the question is, what if the model isn't able to generalize on the text side yet? And that's why we now consider explicitly injecting reasoning capability on the hard text example by training on it. And The question is, will that still transfer over to the hard imaging? Because the connection that we built for the model was on the simple text and the simple image inputs. We are wondering whether the model is able to build that bridge for the hard examples. And the implication here is we expect the LLMs to be stronger in the future. And if our strategy works, then for the LLMs that have stronger text reasoning capability, that can be expected to be transferred over to the image modality as well. Just as a recap, for this part, we will be considering all three of these tasks. These are different from the consecutive table readout because they require much longer reasoning steps, and they also require a lot of compositional generalization, so the model is unable to generalize even on the text format. So here we see that when we train only on simple examples, on text and image, we don't see any generalization happening. It's very bad. That's why we have to modify our training supervision type to explicitly include hard text examples as in distribution training examples. So now the model is expected to solve the hard text reasoning task. And the question again is, will this transfer over to hard image? And the basic answer is yes. So our mix plus supervision, which is just the mixed supervision on simple example plus hard text, is able to improve the S2H generalization capability on hard image examples. But we want to do better. So we now go into some of the methods on how to further improve this behavior. Okay, so let's go back to one of the findings from before. We saw that explicit text conversion before solving the task was very helpful. We had image via text, which is better than mix. So we now consider mixing image via text with the hard text example and see what happens. And we see that image via text plus is still better than mix plus. It generalizes much better, but we still have the same problem. The inference cost is high. So we now consider multiple ways how to utilize this image via text supervision and adapt it to our mix plus supervision. So the first idea is not really tackling the inference time compute, but is reducing the training cost. And the idea is to just take the mix plus model that has been trained on mix plus, and at inference time, we ask it to convert first. And surprisingly, the model's default behavior was to not convert and just directly answer the reasoning solution. But when we ask it to convert first, it does it correctly. Then it goes on to generating reasoning tokens. And this shows that the models trained with Mix Plus have a dual capability of reasoning with and without that conversion. And when it does convert, it actually achieves a better accuracy in the end. So with the convert token, the improvement is significant. But the problem is, since at inference time, we ask the model to directly convert the image to text, the high inference cost is still a bottleneck. So the next question is, how can we internalize this conversion into the model? And we propose a two-phase training strategy where we include a very short pre-training phase on this mixture, where we include an image via text and text. And so the model gets to see both examples and internally aligns the understanding of the two different modalities. It's very short. And we continue on with the mix plus supervision that we have. And doing this is able to improve from mix plus to this aligned mix plus while maintaining the inference cost in the end, because the model's default behavior is to not convert to text first. And so now we have the full plot here, where we had all of these graphs that were training only on simple examples, and the model was not able to generalize. But with the mix plus, mix plus, we were able to transfer the in-domain hard text reasoning capability to the hard image capability. And with our further improvement of aligning with two-phase training strategy, we were able to further boost that performance. So some of the main takeaways from these parts is that the mixed plus model internally already has a dual capability of reasoning with and without conversion. And we can ask it to convert first at inference time, and it improves performance. But we can also achieve an even better result by including a short pre-training phase of aligning it internally. And this two-phase training can further improve this generalization behavior on image and modality while maintaining the inference costs.
So just to, and then we were curious about why this method works. So we look at one study we conduct is to looking at the gradient alignment. So essentially we ask how does training with our proposed mixed supervision helps SUH generalization on images? And the short answer here is that under mixed supervision, the trained models, the training gradients on simple image examples gets more aligned with the gradients on hard image data. So we specifically we look at the loss dynamics here. We look at the average autoregressive loss on the chain of thought token plus the answer token given the input image. And we note that lower evaluation loss on hard image is equivalent to better SUA generalization. So we define the gradient alignment score as this equation. So essentially, it's the ratio of average gradients dot products. We look at both the average gradients given the simple image as well as the hard image. And the interpretation of this score is that higher alignment scores implies like better S2A generalization on image. So for mixed supervision, we notice that it can lead to higher gradient alignment scores, especially when the gradient norms are large. And that observations during the first few training steps, during which the gradient norms are usually large, that observations leads to a more rapid drop in the loss. And similarly, we performed the analysis on the mixed plus as well as the two-phase training. And we observed similar phenomenon that the two-phase training actually achieves higher gradient alignment scores especially when the gradient norms are large. So a summary of this part is that the mixed supervision can enable us to a generalizations on image because it makes the gradients on simple and hard image examples more aligned. And higher alignment scores during the when the gradient norms are large usually leads to more rapid drop in the loss on hard image examples. And similar analysis holds for the two-phase training, which we have already demonstrated it has better performance and it can achieve better gradient alignment. So some of the key takeaways from this talk is, so we noticed that implicit modality alignment can be, and transfer of the reasoning capabilities can happen naturally from autoregressive training. And this is specifically without matching representations. So we have a visualization of the tension pattern that shows that if you look at the animation, the part of the image that the model attends to actually aligns with the underlying highlighted path of the table. And the other takeaways are measuring S2A generalizations on algorithmic proposed algorithmic visual reasoning task offers a more quantitative look at this modality imbalance issue and how we can bridge it. Study of gradient alignments also provides more insights into why what are the important training components. In terms of future directions, the first was to extend the findings to more modality as well as real-world scenarios. So you might ask that all of our evaluations are purely synthetic here. So we found that the skills learned from our proposed synthetic data sets are actually very relevant to improving VLM performance on the real-world benchmarks, such as MMFU and Cheng. But it still remains very challenging to define what are the simple and hard splits for the real-world scenarios because it requires more fine-grained understanding of the underlying abstract concepts.
Sorry, I might have asked this question last time already. Which synthetic type is more useful for this kind of transfer?
So we actually haven't upgraded on that. We just included all the data sets.
Yeah, but which one is more useful? Like, I assume the table readout will be two.
I would say visual analogy is actually one of the like outliers because but grid world and table readout both have components where you have to look at which row you're at and which column you're at, and have to decide which part of the image it needs to be next, like left or up. And I think both are very similar in terms of that capability, and I think both would be important for this.
And another issue was we also find that chain of thoughts plays a very important role in all our experiments. But we also identify another brittleness from the resulted model is that the transfer to a generalization result actually is very dependent on the use of chain of thought template. So we're curious what is the role of chain of thoughts in the cross-model transfer of reasoning capabilities, as well as how to fix its brittleness. And lastly, the ultimate questions for VLM is how can we enhance the integration and processing of visual features? Some of the prior works have already attempted to making the image tokens more language-like or using like more advanced precision encodings to better represent the image. There's also like some efforts in converting to changing from the adapter-based architecture to some more integrated early fusion for better images.